Oh my God.
I
Very
almost thought
questionable.
you forgot about us for a minute.
That is not a far-fetched idea because I am a goober, but luckily I just happened to have been using a very slow computer that was not coming on very fast.
Okay.
Thought for a second he was to say, luckily I just happened to be walking by and I went, oh, I have people waiting on me.
Wait, I'm supposed to do something today. I just
I
passed.
just
Yeah,
so happened to be in town, you know.
Yeah, exactly.
was passing by. Thought I'd come on here and tell you guys about the stars.
I'm still not getting my sleep pattern right. I didn't go to bed till 3 a.m. So that's kind of stinking. But anyways, I'm healthier for it.
No, you're not. Stop deluding yourself. No one's healthy if they miss sleep. Seriously.
We don't need sleep. Poo.
God, I'll sleep when I'm dead.
Exactly.
Sleep is for the
Get some
weak.
serious work done here. Well, does anyone have any questions before we get ramped up in chapter 18?
Do you have any more events where we'll be having to go outside and stare up at the sky?
Uh, I hope. I mean, I don't. We don't have any more labs, but I'm going to try to see if I can't schedule something where we can meet one night. If optional, of course. Y'all would never have to do it, but that would be a nice scenario. I just can't do it in a like in our observatory because it's too small a space. Well, I could because normally I invite 24 to 48, 50 people or something like that, and three show up. So I could probably do it just fine. But I always want to give the option that everybody shows up. So I don't know. I would like to meet somewhere like Pungo or something like that, or Indian Creek Park or whatever that's called back there, Indian Town or Indian Creek Park or something like that.
On what road are you talking about? Because the
Uh,
only park I know around here is Red Wing.
oh yeah, this is like literally one road from North Carolina, basically.
Okay,
There's
so it's
Gall
actually
Bush, and
pretty
then
out
that runs
there.
into Indian Creek, and then Indian Creek. There's a park on the water that's really dark,
Okay.
but it's got the added advantage of snakes being everywhere.
Yeah,
Are
I
you
know the
talking about, wait, you said right before the border?
Yeah, if you're
It's
headed
about
like
like
from Knox Island or something.
London
Munden Point?
Point. Yeah,
Yeah, that might be it. Yeah,
Yeah, that's like right before the border.
yeah.
we'll all show up in our human hamster bubbles.
I've literally been driving by there one day in the 2 o'clock in the afternoon, and a friggin' rattlesnake that was about 4 feet long was kind of ticked with me, aggravating him. I asked him to get out of my lane. He was literally taking up the whole road, and when I pulled up and tried to scare him off, he like got reared back and like snapped at me like he's going to hit me or something. Like I'm in a freaking car. He ain't scared. So that was kind of worrisome.
Back in the day, Munden Point used to be the place to go if you wanted to play on a playscape. They had like a two-story structure you could climb up, and
Oh,
it was
really?
humongous. Yeah, it was the biggest playscape I've ever seen.
Cool.
So that's where
I
you
have to
went.
check that out because I don't know I know the geology or geography of the North Carolina coast much better than I do anything for the Pungo Back Bay area, that sort of thing. But even then, I only know from sort of Grandy north, or excuse me,
Unfortunately,
south, not north.
they took it all down because it was made of metal. Because
Yeah,
can't hurt the new kids.
that's cool.
Can't hurt the newer generations. Only those 80s and early 90s kids got to play on the
Yeah.
leaded paint and the metal.
Remember, like we used to. You young people might not realize this, but all of our playground equipment was friggin' silver. Man, you just go out there and get blistered on the back of your legs sliding down the slide, or try to climb across the
Yep.
monkey bars and get blisters on your hands.
It was like 2 stories tall.
Yeah,
You need an oxygen mask to get to the top of stuff.
yeah. There was one that was like a geodesic dome that was like 18 feet tall, and you could climb all the way to the top. And
Yep.
like,
Normally it had
God
like
forbid if you
cement.
fell.
It had cement. They had
Yeah,
to embed that stuff in cement because it was just like so industrial strength that if
That was the
so
flying buttress for the geodesic dome.
this was before they came out with like these new parks that have like these giant foam pads and then they stick mulch on top.
Kimberly Snyder has a question. Actually, I have no idea if your last name's Snyder. All I see is
Yes.
Snyder.
Yeah, my last name's Snyder. Did you say we don't have any more labs?
Oh, I said no. We still have labs. We're gonna meet every week like we're supposed to, or whatever. I was just saying I don't really have any other labs written up that are to teach you more constellations. So she was asking specifically about opportunities to look at the sky. But no, sorry about that. We still have labs. It's just like I said, I don't
No
have any more
worries.
that are written up like the winter circle, or finding Ursa Major, or using Ursa Major, or anything like that.
I know,
Uh,
Kimberly, I was going to
Okay,
hold
got
him
you.
to that. I was going to be like, you said we had no more labs. We're done.
I'm out of here.
See you later.
Well, we will. I don't know. I might write up one, depending on how. It's been a while since I've been looking at the summer triangle during this semester, so I might make up one for the summer triangle. That's really nice because there's really only 3 constellations. You can easily pick them out, but if they don't come up till 11 o'clock at night before the semester's over, it's kind of a bummer. So I'll check with the stars and see if the alignments are correct. So we can, live in our astrological world instead of our astronomical world. Well, I guess I should go ahead and get started if no one has any other questions. Like I said, we do have a little bit of time before we have to do another test. I think that's what I said last time. Who knows? And it don't really matter too much anymore. Just going on a whim here.
When are you letting the test be posted?
Yeah, the practice test is 15 and 16. It's up right now. Oh, okay, yeah. So
The
that
actual
means,
test.
yeah, we could actually have the actual test this week if we wanted to. Uh, and we're doing 18 right now, so that's not too much of a problem. Yeah, I think I'm going to open the test Thursday. That's what I'll do. So you guys get cracking on that practice test. I'll open it up Thursday and give y'all till Monday to get it done. Does anybody really desire to have it open today, and then I leave it till again Tuesday?
Might as
I'm
well
down.
today.
Yeah.
Go
Yeah,
ahead.
whenever you want to open it, yeah.
I mean,
Okay,
the
I'll go ahead and
sooner the
open it
better.
today. I'll just I gotta. There's always a check. There's not always a check I gotta do. There's always a check I should do, but I often do not, and just trust that it works because it's supposed to.
Don't
So
worry.
I'll
I'll
try to
tell you
trust
if you.
because giving you 2 extra days, but having 2 extra days lost because of that being messed up, then that's a problem. So yeah, I'll go ahead and open it today. If you don't hear from me, then you assume it'll be open probably by your lab time today, and you'll have until a week from today to get it done. Let me go ahead and get started on chapter 18, though. We've already started talking about relativity, and that's really a part of what it's about. It's on relativity and black holes. And your book sort of talks about stars, and then it goes to black holes and then relativity and that sort of stuff. I just jumped right in and started talking about relativity. Excuse me. Relativity is what I was most interested in when I was in college. So that was what I did my undergraduate thesis on. Then I got lucky and did my master's in chaos theory, not because I wanted to, just because I lucked out and got a thesis done literally within the first 3 hours of being in grad school. So that allowed me to be finished a lot quicker and a lot easier. And since I was staying an extra year at my school specifically because I missed one course that only offered every 2 years. I was looking for a way to speed up anyways. So anyways, then my PhD work was in general relativity, or that's what my plan was, and that's the little bit of research I got done was on. So it's one of my areas that I like the best, and it's also, unlike quantum mechanics, when Einstein offered his special theory of relativity and people understood it, it was immediately obvious. Anybody that just took the time to sit down, read it, learn some basic mathematics. Well, basic mathematics. Sorry, that's basic PhD level mathematics was able to do it. It wasn't that complicated. It wasn't that mind bending. Whereas when quantum mechanics came on the scene, the math was in some sense less complicated. In other parts, it was a little bit more complicated. But really, the big deal was it was conceptually so complicated that it took, someone likely as brilliant as Einstein, specifically Niels Bohr, and several other brilliant people to put it all together. I don't know if that was because they weren't Einsteins or if that was because the quantum mechanics was way more complicated to get a grasp of. But either way, it was really, really complicated, and I just don't enjoy it as much. So we're going to talk about the relativity aspects. I already told you about the principles. The first principle is that the laws of physics are the same for all inertial observers, and I explained to you. And I explained to you how in Einstein's idea, when he's talking about inertial reference frame, he's saying any frame where there looks to be no force acting on an object, yet that object is accelerating, then that's a non-inertial frame. So just looking at, for instance, a video you see of a ball being held by a person in an elevator, and then if the person just drops the ball accelerates downward. Okay, to us, we know that that's just gravity. We see yep, it fell a distance of 5 meters roughly in the first second. It fell a distance of 20 meters in the total of 2 seconds, and so on and so forth. That's clearly 9.8 meters per second. So that would look fine to us, and we probably still try to call that an inertial frame. Einstein's saying, no, that's not an inertial frame because that evidently has some force that we can't see acting at a distance because it's causing it to disobey the law of inertia, Galileo's law of inertia or Newton's first law of motion, because that object clearly accelerated. So really what he was doing was taking out gravity when he called for the special theory of relativity. And like I said, the difference between the first postulate in special theory of relativity and that first postulate in general relativity is that the first postulate has the word inertia in special relativity. So the laws of physics are the same for all inertial reference frames in special relativity. Then you have the more general case of general relativity, which means it's bigger, more encompassing, covers supposedly everything. That one has the laws of physics are the same for all observers, full stop. Okay, so it just left off the word inertia. The second principle of special relativity was that the speed of light is a constant, independent of the motion of the source or the observer. And I explained to you how that's like, you throwing a ball in the direction that a truck is driving while standing on the back of the truck. If you happen to throw that ball at the speed of light, then you're not going to be adding that speed of light to the velocity of the truck, no matter how big the velocity of the truck is. Specifically because the speed of light is the speed of light independent of the source, the motion of the source or the motion of the observer. And if you are throwing that ball at the speed of light on the back of that truck, and that truck is going 99.5% of the speed of light, and it's headed for another truck that's going the opposite direction, like in a head-on collision at 99.5% of the speed of light, clearly those two trucks are going super, super fast towards each other. And when that other truck tries to measure the velocity of the ball I threw, he still finds it's the speed of light. Okay, that is absurd. And when we take that into account by making things like time clocks, so if we want to light clocks, if you want a clock that implements the special theory of relativity, then you've got to have light involved some way. So what Einstein did was created these little clocks where basically you send a beam of light up, it would hit a mirror and bounce back and come back. And when it returns, that time period from here to here to here, that time period is one click of time or 1 unit of time. By doing that, he could explain very complicated problems with little diagrams of trains. So let me start off by giving you one of those little diagrams so that you can see one of the fundamental results of the special theory of relativity, specifically that simultaneity is relative. Simultaneity is not an absolute thing. So here we go. So imagine two train cars, and this is an idea taken straight from Einstein, in fact. Imagine two train cars let's say this bottom train car happens to actually be moving at 86.6% of the speed of light. When beta is equal to the square root of 3 over 2, which is approximately equal to 0.86603, then V is equal to beta C, that's the definition of beta, equals 86.603% of the speed of light. That's really what I'm talking about here, okay? So that is really nice because when that's the case, there's this factor called gamma, which is defined to be 1 over the square root of 1 minus beta squared, which is obviously 1 over the square root of 1 minus V over C squared. Beta equals square root 3 over 2 makes gamma equal to 2. So in other words, this factor right here is a relativistic factor, and it causes things to change by a very specific amount. In this case, a factor of 2. So that's just something neat to think about that we're going to use later when I talk about 2 of the other ramifications. But right now we're imagining this bottom train car happens to be moving at V equals root 3 over 2 times the speed of light. Okay. So 86% of the speed of light, pretty darn fast. Now, it happens to be at the instant that is right here, it happens to be right next to yet another train that's identical in size, but that train is in fact sitting still compared to us, anyways, relative to us, okay? Now, what happens is there are bolts of lightning that hits right here and right here, supposedly at the same instant, okay? They hit right here and right here, and there's this little mechanism where when the lightning hits here, it automatically sends a signal over to here, which is a little light, if you will. And it also sends a signal over to here, which is a little light. Similarly, this one has the same sort of setup, sets up a little light, and this one sets up a little light. So what happens in this top one's frame is this. You're sitting there, all of a sudden lightning strikes, and then in your train, you see the little light bulbs send out a pulse of light, and you're dead center sitting here. That's maybe your detector, or that's you. Why did I write E on the end of you? Holy crap. I don't know what that was about. Anyways, the next wave of light was this was the first wave of light, say, and this is the first wave crest of light. Here's the second wave crest of light. So the light's actually moving that way and that way. That's really what's happened, is this lightning bolt caused the light here and here to send a pulse of light this way and a pulse of light this way in these two things, okay? So the actual very first light might be said to arrive right here at the exact same instant, and this will be called train A. This will be called train B. So this one is A. So in train A, if you're sitting in the center or you're the detector, then what you would conclude is that this beam of light and this beam of light arrived at the dead center at exactly the same time. Therefore, in your frame of reference A, you say that these two lightning bolts were simultaneous. Okay, so does that seem obvious to everybody? That would clearly happen. The light beams would go this way, and the light beams would go this way. And since this is the dead center, that clearly they would arrive here at the same time. Well, here's the other part. When we look at part B, when we look at train car B, what we see, well, I should try to make it the same length as the last one. What we see is electricity going into this light bulb and electricity going into this light bulb. And then a split second later, since the train is actually moving in our frame, relative to us, in other words, a split second later, we see the train is now over here. And because the center point has moved over that way a little bit, what has happened is this little beam of light has gotten this far from the front because this little spot right here was moving towards it, right? It released a little beam of light, a little light wave, if you will, going this way. But because the train is moving this way, this center part actually moves towards that beam of light. Now, you might say, well, wait a second. The train is going this way, and the light source was going, and the light was being fired this way, so that the velocity of the light should really be c minus the velocity of the train. But remember, the velocity of light is independent of the motion of the source of the observer, going to be measured as c. So this speed is still c, and the distance is actually shrinking. So in this frame, the person concludes that this bulb sent the light first. Now, by this time, we've really only gotten to say this light bulb back here in the back. Maybe he's only gotten this far. And the reason being is because when this one hit, it sent out a little pulse of light. Well, by that time, this center spot had moved way over here. Now, again, you might say, well, wait a second. On this end, the velocity should be the speed of light plus the velocity of the car. But no, again, the special theory of relativity says the speed of light is a constant independent of the motion of the source and independent of the motion of the observer. So ultimately what we find is that velocity is still c. So it takes longer time for it to get from here to here. And in this person's frame, in frame B, we conclude that the lightning bolts were not simultaneous, but rather this front lightning bolt struck first and the second lightning bolt came second. And the last slide, of course, on this would be, I'll draw it down here since I put my words in the way. The train car is now over here. Remember, this guy is actually moving with velocity v. The train car is over here. Now what's happened is finally this beam of light has hit the center, and now you finally say the rear bulb, which if you don't think you're moving, it'd be weird to call that the rear anyways, but still the rear bulb fired second. So this is a quick proof, if you will, that under the special theory of relativity, specifically the postulate with the constants of the speed of light, independent of the motion of the source and the observer, simultaneity is no longer a universal thing. So you can have something be simultaneous in one frame, but not simultaneous in another. An example of this is the ladder and the barn paradox, which I'll talk about in a little bit. But the main thing is you really can't do the ladder and the barn paradox until you see some other results that come from the special theory of relativity. So here's another result of the special theory of relativity. So let's do another train car again. This time I am going to cordon off the area from where we just finished drawing, separate it from here. Okay, so in this scenario, we're going to have one train car, but we're going to look at it from two perspectives. We're going to look at it first from the perspective of the person on the train. And second, we're going to look at it from the perspective of the people on the side of the track watching the train go by at some speed v that might be 86.6% of the speed of light, but doesn't necessarily have to be. Okay, that just gives me a concrete number that we can think about. So on this train, so let's say rider's frame. In the rider's frame, basically what you have is a little clock here at the back of the plane, at the back of the train. The distance from the light and the mirror is d. And in fact, what a unit of time would be, and we'll call this, by the way, we'll call this unit of time delta t. Now, we're actually going to call it delta t0 because it turns out both the beginning of this event, namely a light beam shooting out, and the end of the event, which means it's bounced and then returns, occurred at the same point in space. According to you, on this train, it happened right here, right next to you. So you're sitting here in Indian style, or crisscross applesauce or whatever, and you're sitting right here in your frame. The beginning of the event, which was the starting of the timer, to the end of the event happened at the same place both times. So that's what we call the proper time. Okay, and that proper time, if you remember, velocity equals distance divided by time. You can say time, if I just trade places with time and velocity, you get time would equal distance divided by velocity. So you can see that the time required for this is really 2d, because it's got to go up d and then back d, and then over the velocity, which of course would be the speed of light. So that's what the actual person on board the train sees. So that's the train rider's frame. And then it bounces back here, of course, and comes back that way. And at the end, that's the time period delta t0. Now, from our frame on the side of the track, what we see is this. So the train is here at one instant, is then here at another instant, and then finally at the end of the time interval, which in this frame we're going to call delta t as opposed to delta t0. This is the end of the time interval, delta t. Now in this case, what happened was we saw the light do an entirely different motion from what we saw in the first case. In this case, the light went from here all the way to here, and then bounced from here and went all the way to here. Now you might say the distance it traveled was L, and that would be fine. And then of course, this distance is still D, right? So the distance the train traveled was L, but since we know the train is moving at a velocity V, then we could say that L is equal to the velocity of the train times delta t. Okay. Again, that velocity might be 0.86603, the speed of light, and that would be fine. Now, in this case, you'll see that the distance is quite different, and there's some algebra that's going to play in here, but all I want is the formula, and I'm not even going to make you use the formula. I just wanted to let you see how easy it is to actually come up with it. You don't need any fancy math, fancier than high school algebra 1 or maybe 2. So in this case, the time period is actually the distance traveled, which now is the hypotenuse of this triangle plus the hypotenuse of this triangle. Notice you can actually imagine a triangle whose leg right here is L over 2 and whose leg right here is L over 2, but this one is D. So it's going to be 2 times the square root of D squared plus V times delta T over 2 squared. So just using the Pythagorean theorem, we can get that distance. And then, of course, we're going to divide that by C, because that's the distance divided by the speed of light. Now, it turns out if you take the time to solve this for D and then plug that in for that D, you get this really cool expression that says that delta T is equal to delta T 0 over the square root of 1 minus V over C squared, which we often call gamma times delta T 0. So remember, I told you that when velocity is root 3 over 2, or 0.86603 times the speed of light, right, that gamma would actually be 2. So what this means is that the time we measure for this guy to go from here to here, in other words, this beam of light to go from here all the way to here, is this time t. And compared to the proper time, which is what the person sitting on the train measured, if that was, say, 10 minutes, then this person is going to say, no, your 10-minute interval was actually 20 minutes in our frame. And because the first principle of relativity, the laws of physics are the same for all inertial observers, both the person watching the train car go by on the side of the track that says the time interval was 20 minutes and the person that was sitting on the train that said the time interval was 10 minutes, both people are correct. Okay, that's a ramification of relativity, and that's called time dilation. And it means that moving clocks run slowly. What do I mean by that? Well, the example I usually use is, imagine you did this cool experiment again with the ice cream that I told you guys about. That you found that this particular ice cream cone, when perfectly made, always takes 10 minutes. If you set this ice cream cone on here, and this person watching it who's riding on the train, he would conclude that it's 10 minutes long, and that would be just fine. Okay, that's the proper time. That's measured by a person that sees both the beginning of the ice cream melting and the end of the ice cream melting occurring at his same point in space, i.e. right next to him, so that he's measuring proper time. And then when we watched it from the side of the track, what we would see is, oh, wow, that's really nice. His ice cream lasted a whole 20 minutes. Okay. Now, if you were to say, wait a second, what about his perspective? Well, from his perspective, he sees the train track and the train station flying by this way at 0.86603 times the speed of light. And he measures his ice cream taking 10 minutes. But because you guys are moving by at 86.603% of the speed of light, he sees you standing on the side of the railroad track holding an ice cream that lasts 20 minutes. And you're both right again. Okay. So from his frame, the Earth and the train station and the train track is moving this way at 86.603% of the speed of light. And their clocks are running slow. And from our perspective, he's going this way at 86.603% of the speed of light, and his clocks are running slow. And that clock could be like a human heart, for instance. So if you have trained yourself to do to get exactly 60 beats per minute of your heart during a given minute, then if we watched you riding by, we would detect that it actually took basically what you would call 1 minute on here. We would actually count 120 beats. And you would actually say, no, it was only 60 because it was a 1 minute interval. So that's one of the ramifications. It's time dilation, and I left off an N down here. But time dilation allows us to come up with the other paradox that's actually more famous. And I mentioned that before. That's the twin paradox, where you have two twins, say on planet Earth, let's say me and my brother, and we're twin brothers now instead of being 7 years apart. And we happen to jump to a spacecraft traveling at √3/2 times the speed of light. Let's say me and bro, and my bro teleports to here, zoop, and then flies all the way to the Alpha Centauri system, at which point he catches a ride with another spacecraft, also going √3/2 times c, but in the opposite way. So he teleports over to here and then flies all the way back here. And then when he gets back here, he teleports back down to here. Now, Alpha Centauri is about 4 light years away, 4.2 say. And because we're going only 86% of the speed of light, we on Earth would say your trip would take a little bit more than 4.2 years to get there. Let's say it would take 4.5. That's probably not the number, but that's just a rough estimate. So we conclude it took 4.5 years for him to get to here, and then he teleported over there, and it took another 4.5 years. So he come back, and of course I'm now 9 months older, or excuse me, I'm now 9 years older, and my brother is in fact not older. In fact, he's just 9 years divided by 2, so he's 4.5 years old. So me, 9 years older, and my bro is 4.5 years older. Now, a lot of people just stop there and call that the paradox. That's not the paradox. That's the fact. Okay. That really is what would happen. And it's exactly right. And yeah, we would be forever the twins who one's older than the other. Now, where the paradox comes in is when I don't like the idea of being 9 years older, where my brother's only, 4.5 years older. I try to claim that in reality, Alpha Centauri and the Earth flew over here. And I of course, sat perfectly still, and then it flew back that way. And because of that, now I'm the one that is actually 4.5 years older, and my brother's 9 years older. Obviously, that's something that you could measure, right? When you get back, you can tell which one of us is aged by 4.5 years versus 9 years. So there should be some definitive answer, and the definitive answer is my brother is definitely the one that's younger. And the reason why is you can tell he's the one that moved. It's not a relative thing. It's not, just to say, oh, well, in my frame, I moved to the right and then came back. Whereas in Brian's frame, he moved to the right and came back. No, you can't say that, because all it would take is a pair of fuzzy dice to fix it and show you which one's right. If my brother was holding fuzzy dice and he transported from here to this spacecraft, obviously the fuzzy dice would sling back that way, because Brian was sitting perfectly still. Now all of a sudden he's going, some 170,000 miles per second, right? So clearly the fuzzy dice would swing back this way. And then when he got here, they'd really swing back, because he's going 170,000 miles per second, and then starts going immediately 170,000 miles per second back this way. So we can tell which one actually moved. Ergo, I can't make the argument that I was the one moving, not my brother. Okay. So that's the settlement of the ladder, or the twin paradox. And the ladder and the barn paradox is an entirely different scenario. And in order to do that, you have to realize that there's another equation, and it's called length contraction. And in length contraction, it basically says that the length, again, this doesn't have a 0 on it, so it's not the proper length, is equal to the proper length divided by that same factor gamma. Now, the proper length is the length measured in a frame in which the object's not moving. So if you're measuring the length, say, of a spacecraft, then you need, if you want the proper length, you have to be the person on the spacecraft doing the measuring, right? The person that sees the spacecraft flying by, they're measuring the non-proper length. And since gamma is always greater than or equal to 1, you know that I'm dividing the proper length by multiplying in the case of time dilation, but dividing by something greater than or equal to 1 of the proper length, then you see that L is actually going to be shorter than L0. So the big result there is that moving objects shrink. And I'll add this caveat. So moving objects shrink parallel to its motion. What does that mean? Well, if you had like the old police cars, which were Lincoln Continentals, they were like super long. In fact, when I met my first wife, who was my girl's mother, her mom and dad had a Lincoln Continental. And she calls it a cruise ship because it was so freaking big. You know, big 4-door. The hood's like 8 feet long, some god awful stuff. Well, if you see this traveling by, say at V equals √3/2, again, just for concreteness to give you a number, what it would actually look like would be exactly half this width, but exactly the same height. So what we would see is the tires would be ovals. This windshield would be almost vertical. This windshield would be less close to vertical, but still almost vertical. Notice how the height hasn't changed at all, but the length has shrunk by a factor of 2. That's what happens, okay? So if we're sitting here as this car is going by at 86.6% of the speed of light, then we see this car, which might have been 12 feet long, now it's all of a sudden 6 feet long. But if it was 4 feet tall, it's still 4 feet tall. So I'll mark this as like 6 feet, 4 feet. I'll mark this as 4 feet and 12 feet. Okay, I have no idea what the true lengths and heights of those vehicles are. I'm just giving you numbers to think about. Now, if you jump to the car's frame, now according to the car's frame, the city is flying by, and lots that are, say, 60 feet wide now are 30 feet wide. And, you know, a Home Depot that's 240 feet wide is all of a sudden 120 feet wide, but exactly the same height. So in this one's frame, everything else is shrunk. But in our frame, when that one's moving, that thing has shrunk. So that's length contraction. Those are two of the major ramifications. The lack of simultaneity, actually, I should say 3. The lack of simultaneity being universal. 1, moving clocks move slower, and 2, moving objects get shorter. Those are 3 major ramifications of the special theory of relativity. And the ladder in the barn paradox goes like this. I usually soup it up a little bit. So you imagine a little barn. Okay. I'll make it like an Aberdeen barn so it has a fancy roof, a gambrel roof, I think is what it's called. Anyways, and let's say this particular barn is 10 foot wide from the front to the back. Okay. And it has a ladder leaning against it. That is, in fact, 20 feet long. Okay. So this is on a farmer's land, And of course, the farmer who's been farming for some years, he sent his son off to college. His son went to NC State. He's learning about agriculture and other things. And one of the classes he had to take was physics. So now he comes back, and like you normally do when you first get in college, you all of a sudden feel like, wow, I'm learning all this cool stuff. And you go home and you want to tell about all the stuff maybe stuff that your parents hadn't heard of, or your brother or sister or whatever. So you're sort of bragging about it. And sometimes you even get a little cocky because you don't realize, some of these people might have went through the same things and just have forgotten a lot of that stuff. But anyways, the son comes back. He's disgusted to find out, having, now being knowledgeable about physics, having one course. He looks out and he's like, Dad, why haven't you taken the time to put that stupid ladder in the barn? And Dad said, well, son, I don't know what they're teaching up in NC State now, but back when I went there, they taught us that a 20-foot ladder don't fit in a 10-foot barn. He said, yeah, Dad. Well, the world's changing, okay? There's a guy named Einstein, and he wrote Special Theory of Relativity. So, yeah, all it takes for us to fit that ladder in the barn is us to move the ladder at 86.603% of the speed of light, and then it'll shrink the ladder from 10-foot long, from 20-foot long to 10-foot long. And the father says, oh, yeah? He said, yeah. He said, okay, son, well, I'll tell you what, I'll let you do the honors. You're younger than me. So I'll let you run with the ladder. And as the ladder just fits in there, I'll close the door right behind you, and we'll have put the ladder in the barn. The son says, okay, haha, you're gonna feel like a fool. And the father's just giggling. So what happens is the son, falling for the bait that his father has left, is running with all his might, holding the ladder like this. And the son is running at v equals the square root of 3 over 2 times the speed of light. And the father's over here just standing by watching, laughing his butt off, and you don't know why. But all of a sudden you realize why, because now that the boy is running, he realizes, oh crap, the ladder's 20 feet long, because he's measuring proper length. In his frame, the ladder's not moving with respect to him, so it suffers no contraction. He's like the car seeing the buildings ride by, in which case now the shed is a measly 5 feet wide. So what he sees is, oh crap, the darn barn is now 5 feet long, and now my ladder's 4 feet long. It's definitely not going to fit in there. So as he runs, he gets his front edge of the ladder to here, say, and then he blows right through the back, leaving a Wile E. Coyote-esque hole in the back of the shed. And then the back edge lines up with the with the front of the shed. And his dad goes and closes the gate. And he's like, what the crap's wrong with Dad? Clearly he knows what just happened. And at the end of the day, what is the right answer? Did the ladder actually fit, or did it not? And this is actually solved by, again, the lack of simultaneity. Because what it means, at least in this particular instance of the ladder fitting, is that the front edge of the ladder is lined up with the back edge of the barn at the same instant that the back edge of the ladder is lined up with the front edge of the barn, and the door closes. Those two events are simultaneous. In fact, they're simultaneous in Dad's frame, because in Dad's frame, he did see his son shrink this way, and he did see the ladder shrink down to 10 feet. And he did see that when his son was in the middle of the barn, the front edge of the ladder was here and the back edge of the ladder was here, and he closed the door, and it fit for that split second. Of course, as soon as he came to a stop, the ladder would grow and blow out the front and back, or he couldn't come to a stop instantaneously and he'd just run all the way through. But the main thing is he did, for one instant, fit the ladder in the barn. So you want to simplistically say, well, either it fit or it didn't fit, and that's not the case at all. It turns out in the father's frame, it did fit because those were simultaneous events. But in the son's frame, those two events were not simultaneous. The front edge got to the back edge of the barn. Then sometime later, the boy got to the back edge of the barn. And then sometime later, the back edge of the ladder right here got to the front edge of the barn, and Dad closed the gate. But that was all a sequence of events that were in no sense simultaneous. So there is no paradox. What you thought was a paradox was only possible to be a paradox if, and that's only if, simultaneity is not relative. So we already learned that simultaneity is relative. So that solved the ladder and the barn paradox. Any questions on that? So those are some kind of neat things that come from relativity. Relativity also gives neat things like the momentum, something different. In physics, we call momentum P equals mv, but according to relativity, momentum is actually P is equal to gamma mv. In regular physics, we say that kinetic energy is equal to 1/2 mv squared. In relativity, kinetic energy is equal to gamma minus 1 times mc squared, like that. And the total energy E total, according to special relativity, is just equal to gamma mc squared, which turns out to be E squared equal to P squared C squared plus M squared C to the 4th. So that's a whole nother different group of expressions. So there's a lot of things that happen in going from the classical world, which is the world of Newton and Maxwell, to the relativistic world, which is the world of Einstein and also Maxwell, because Maxwell's equations were right regarding relativity from the get-go. So these are some things, again, you don't have to use any of these things, but you certainly should know that a moving object shrinks parallel to the direction that it's moving. A moving object's clock moves more slowly, according to us that think it's moving and think we're sitting still. Another thing that they sort of say, which I try not to teach it necessarily, but it has its place. As you try to accelerate an object, F, according to Newton's second law, is delta P over delta T, okay? Well, when you look at that, one way of looking at it is the way where F equals ma is Newton's second law. That's another way of writing it. You could try to address the fact that it's infinitely hard to reach the speed of light if you have any mass, and you would maybe conclude that's the case because m relativistic is equal to gamma times m0. That's when you're talking a relativistic mass, and I don't believe in it because mass is a scalar quantity and shouldn't have any transformations from one coordinate to the other. So I don't like using that, but that's how you have to explain it here. But if you use relativity, Newton's second law in this form, then you have P is gamma mv, so the gamma is already fixed in there, and what you realize is, yes, the faster I go, because gamma, remember, that's actually related to the speed of light. Gamma is defined to be 1 over 1 minus v over c squared to the square root under that, okay? So this v getting larger and larger actually makes gamma get larger and larger and larger. So as v goes up, gamma goes up as well, but it's not a straight linear thing, so I can't write a 2 here and a 2 here or something like that. The main thing is the higher the velocity, the higher the gamma. So lo and behold, the faster you go, the larger your momentum gets, and therefore the larger the force is needed to make it go change as much as it did before. So maybe it took 100 newtons of force to get you to go from 0 to 20 meters per second. But now it's going to take 110 newtons of force to get you to go from from 20 to 40. And then it's going to take even more to get from 20 to 60 or 40 to 60 and so on and so forth. So you see that the only things that could possibly reach the speed of light are things whose mass is 0, because otherwise it's going to take an infinite amount of energy, or it's going to take an infinite amount of force. obviously looking at this, gamma can get as large as infinity, because if this actually becomes v over c, and v becomes the actual speed of light, then you get 1 minus 1 in the denominator, and this number is approaching infinity. So as v gets closer and closer to the speed of light, gamma becomes closer and closer to infinity. So you'd see it would have an infinite amount of energy if the mass is not zero. But it also introduced us to this little term right here, which if you take the square root of it, you'll see is E rest is equal to mc squared. And Einstein, when he wrote his paper, he literally just sent this in as an appendix the next day, because he just discovered it shortly thereafter. And that turned out to be the equation that probably every person in the world, almost every person in the world, can recall from physics. It's one of the few equations that people recall. And it's basically saying that the energy is equal to mass times the square of the speed of light. It's a conversion factor, if you will, between matter and energy, because it turns out that this is true when any energy is obtained. So for instance, if you take a gallon or 10 gallons of gas and you put it in your car, okay, then you crank your car up, which by the way was completely empty beforehand, and you drive it until that gas runs completely out, and you calculate exactly how much energy has been used in accelerating your car, pushing your car against the air, all that good stuff. And you calculate all that energy, and then you weigh every bit of dust that came out, dust and gas and debris that came out of the tailpipe, and every bit of dust and gas and debris that was stuck along inside the engine from that tank of gas. When you're done with all that and you do M final minus M initial, you'll find that that doesn't equal zero. Now it'll equal 0.000000000, but then those numbers beyond that might not actually be zero, are not going to be zero. So it's not equal to zero. So what you end up getting is that the change in energy is equal to the change in mass times c squared. So if you take that difference in mass and multiply it by the speed of light times the speed of light again, you'll actually get, remember that energy that we calculated for the car moving? That's exactly what you'll get. So it's true in all cases. E equals mc squared is a fact of nature, no matter what. When energy comes from, bonds being broken between carbons and hydrogens, which is what happens when you burn fuel in your car, that energy comes from a direct loss in mass. Now that mass we used to couldn't detect, and we still pretty much can't on that scale, but we can see it every day, for instance, in the sun when nuclear fusion takes place, because in nuclear fusion, you take 4 protons, they combine to form 2 protons and 2 neutrons, and you find that the mass of the 2 protons and 2 neutrons is different from the mass of the 4 protons. And that mass difference times c squared, subtracting out the energy for the positrons that are created and for the neutrinos that are created, the rest of that energy goes as actually radiation that's coming out to us. Well, the positrons actually give off gamma rays too, or give off photons as well, because the positron is going to combine with an electron and then give off 2 photons. But either way, that energy coming from the sun comes from this E equals mc squared, but it's always true. If you increase your potential energy by climbing up a flight of stairs, say 10 feet, then you can find somewhere some loss of mass that is the result, or is the cause of you actually gaining some energy. And then when you move back down, there should be some increase in mass that accounts for that loss in energy you had. Okay, so that's just special relativity. When we go to general relativity, like I said, the laws of physics are the same for all observers is one change. The other change is something called the equivalence principle. And the equivalence principle just basically says that you can't do an experiment, at least on a small scale, that shows you the difference between an object accelerating and an object experiencing a gravitational field. So let me give you an example of that. If you imagine being on let's say an elevator, that's also a rocket ship. In other words, it's a rocket ship shaped like an elevator, okay? But it's built so robustly that it's completely soundproof. So if I actually fire my rockets in this spaceship slash elevator, you can't tell it. You can't feel any vibration. You can't hear anything or anything. So if you're standing right here and holding a ball, and you drop the ball and it accelerates downward, and you say A is equal to 9.8 meters per second per second. If you reach that conclusion, this might be because the rocket ship is accelerating upward at 9.8 meters per second, but it also might be because this rocket ship is sitting on the surface of the Earth. Okay. So the equivalence principle says you can't tell the difference between these two, at least on a small scale. Now, if you imagine this elevator being like this big, say, then if you did this experiment over here, you would see the ball falling this way. And if you did the experiment over here, you would see the ball falling this way. And there, of course, you'd see it falling this way. So on a big enough scale, yeah, you can tell the difference between quote unquote a gravitational field and a accelerating reference frame. But on a small enough scale, which is the scale that we use when we write differential equations, you can't tell the difference between the two. Once he had that, Einstein knew how to solve the general theory, or how to solve the problem of gravity. He just had to treat space like it's a accelerating reference frame. What he ultimately did was, first, to make the first law work, you know, the principle that the laws of physics are the same for all inertial observers. Well, he had to write the laws of physics in what we call tensorial form, in a tensor form. And that's because tensors transform a very specific way from one coordinate to the other. And when you do that transformation on Einstein's equations, you get Einstein's equations in all frames. And that's just the way tensors behave. So that's how he took it into account. And that's why I had to do sort of some complicated mathematics that, like I said, you don't get to start learning until maybe, if you're a really good math student, you might learn in your junior or senior year of undergraduate. But if you're not that great of a student, or if you're at a you know, not a frontline university like Caltech or Stanford or MIT or some of the universities, Oxford and Cambridge in Great Britain, or some of the more impressive ones in China or India, if you're not there, then you never get to learn that math as an undergraduate. But as a graduate student, you might be able to get it. If you get a PhD, you're probably going to have at least 1 or 2 courses in it. So Einstein did that. He made up his equations to be consistent with the laws of physics are the same in all inertial observers, in all reference frames, not just inertial reference frames. He accomplished that by, again, making all the equations in tensorial form. There's a covariant principle that they're actually using there. So if you run across that, that's what that means. It just means in tensor equations. And then he basically concluded that space was in fact 4-dimensional. It has a X that's left and right, say, a Y that's in and out, say, a Z that's up and down, say. Technically, it should be right, forward, and up for a right-handed coordinate system. But the main thing is each of those directions are perpendicular to each of the other ones. So left and right is perpendicular to forward and backwards. Left and right is perpendicular to up and down. Up and down is perpendicular to forward and backwards as well. So all of those are mutually perpendicular. Einstein found that there's yet a 4th dimension. It actually turns out to be time, that's mutually perpendicular to those 3. Now, obviously, you can't see it, right? We've sort of used up all our 90-degree angles in making up this, but we got to look for another 90-degree angle that's 90 degrees to left, right, 90 degrees to forward, backwards, and 90 degrees to up and down. That's our time dimension. When he implemented that, he found that that space has the ability to not be flat. And in fact, that space, the way MTW, which is Misner, Thorne, and Wheeler, that's the Bible of relativity. It's this really big, thick black book called Gravitation. And it has MTW written on the bottom because the authors' names are Misner, Thorne, and Wheeler. Thorne just won the Nobel Prize, by the way, him and Barry Barish, and I forgot the other guy's name. Anyways, they all won the Nobel Prize for detecting a black hole gravitational wave that came from Einstein's equation. Well, those people wrote this book, and they said matter tells space how to bend, and space tells matter how to move. So Einstein's equations basically do that. Einstein's equations say, hey, here's a mass. Well, because of that mass, that's going to make the space around it warp, sort of like a trampoline does when you put a bowling ball on it. It's going to warp. It's going to get a pucker. Okay. And then an object like a BB flying by, say the bowling ball on the trampoline, flying by will get into that little depression in the actual trampoline and go around in a circle. Not because there's some force pulling the BB towards the bowling ball. There's not a magical gravitational force between the bowling ball and the BB, but rather there's a force caused by space in some sense. You can just say space is causing it to move funny, but you can also think in the trampoline case, there literally is a force that the space, the trampoline, is applying to the ball. It's making the ball tilt over and roll over this way. But that's what matter does, is matter obeys what space tells it to do, and it follows a geodesic, a path of least distance is what we normally refer to as a geodesic. But in relativity, things follow lines of least time as opposed to least distance. And in doing that, that happens to be in proximity of our sun in elliptical orbits, because the space in 4 dimensions is dented by the mass of the sun. And you also get things like there's a redshift caused by when something say falls into a gravitational well. So if you're up at the height, say, of the International Space Station, you jump off and fall towards the Earth, then you're going to speed up, and your energy is going to basically get lower and lower and lower. That energy, of course, gets lower and lower and lower by changing the wavelength to higher and higher wavelengths. So we'll see you become redshifted as you fall into a gravitational well, or another way of looking at it is you can say you become blue shifted on the way up, or red shifted, depending on what kind of energy you're talking about or whatever. But that's one of the ramifications, is you get this change in color as a change in wavelength of light emitted as you go into different gravitational fields. Not only that, the gravitational field causes time dilation, just like just motion did, but now you've got a time changing just as a result of being in a different gravitational potential energy. We have to use general relativity to correct for our GPS. Like if you're using Google Earth, that means you're actually using the general theory of relativity, because Google Earth will tell you fairly precisely to where you are on the surface of the Earth within meters, and you can't get that precision of less than centimeters and stuff unless you correct for time issues that happen as a result of general relativity. So there's a lot of neat things, and one of the things that was predicted was an object that's so massive that that light can't escape it. Well, it turns out, here's the deal. In terms of everyday energy, I'm going to give you another equation, but this is the one where it really doesn't matter. I'm not requiring you to do this. It's fun to do it, but it's not really required. If you talk about the total energy of an object, let's say something trying to leave the surface of the sun, okay? We'll say we're going to give that thing kinetic energy. I'm using classical kinetic energy. We're going to give that spaceship kinetic energy 1/2 mv, and I'm going to write v escape squared. Okay, that's the kinetic energy that a rocket ship might have Dang it, I'm running out of time. Let me finish this up. The potential energy the rocket would have would be G times the mass of the rocket times the mass of the sun over the radius of the sun. Okay, that's the potential energy. And of course, if you allow this, if this is really the escape velocity and it gets infinitely far away, it will come to a stop. So the total energy will be zero. In other words, all your kinetic energy went into overcoming this potential energy. When you set those equal to zero, equal to each other, because it's equal to zero, you get G M sun over the radius of the sun, like that. Okay, you can tell clearly that when this happens, these two masses cancel out, and you end up getting the escape velocity is equal to the square root of 2g times the mass of the sun over the radius of the sun. And that is the actual formula that we found earlier for the escape velocity in your book. I just didn't make you use it. Now, if you allow the escape velocity to be the speed of light, then you can find that the radius of the sun would have to be given by, now if we square both sides, I'm going to get I'm going to get c squared, because now v is the speed of light. So I'm going to get c squared. You can put it up here, c squared times 1/2 is all this. I want to solve for the radius of the sun. The radius of the sun is going to be, well, actually, let me just do it on the line below. I'll say 1/2 c squared is equal to g m sun over r sun. So r sun is equal to 2 gm sun over c squared. And it turns out that is the source shield radius. Even though we did it with classical physics, that gave us exactly the right result. That is the radius of the event horizon of a black hole. And in fact, if you put in the numbers for the sun, you'll actually find that a black hole, the size of the mass of the sun, is actually going to be like smaller than Earth. And you can sort of use that to find out the radius of all black holes just by using this formula over and over like your book does. But I just wanted to show you that. So that's really it as far as how black holes work. I will cover the rest of chapter 18 next time. And that's basically it. So let me, actually, no, I'll finish it today in lab. That's what I'll do. Because the lab that I gave you last time obviously takes a lot of work. So I want to give you some more time for that. So what I'm going to do is we'll meet at 1 for our lab, and I'll finish up chapter 18. And that'll be all you have for this week for the lab. Okay. I'll let you guys go. I'll wait for the last one to leave. Everyone's free to leave.
Professor,
Yes.
could I speak with you in a breakout room?
Yes. Anybody else need me? I'm going to put a breakout room up real quick for Amani, and I will be right back if you are. Do you have a quick question before I go to the breakout room for anybody else, though?
No, but you may want to stop recording.
Yeah, that'd be good. Actually, I think it stops when I go to the room, but yeah, I should always do that anyway.